All right, so our next speaker is Chun Chau, and he's going to talk about the simple essence of Boolean-Algebraic subtyping. Go ahead.
Hello, everyone. Welcome to my talk, where we are going to discuss the simple essence of Boolean-Algebraic subtyping, where we are going to explore the semantic soundness for algebraic union, intersection, negation, and Equi-recursive types. So first and foremost, what are union, intersection, and negation types? So in the simplest term, when two values flow together, they give rise to a union type, which we denote with this square cup. And when a value is used in two different ways, it gives rise to an intersection type, which we denote with this square cap. And when a value cannot be given a certain type, we can give it a negation type, which is denoted by this negation symbol here. And we call all these Boolean algebraic types, and they give rise to, they admit a very natural subtyping order. And as we're going to see, they have a lot of useful use cases. And in the design of a type system with intersections and union types, one central concern is how should the unions and intersections distribute over type constructors. So let's take a look at this question from the point of view of the most common type constructor, the arrow. In literature, there have been a few different proposals for how unions and intersections should distribute over it. For example, intersection over functions may distribute over the result type, or it may distribute over the argument type, where it becomes a union due to the contravariance of the argument type. Or we can have both of the above. Furthermore, we can also admit a rule that generalizes both rules, where a union is distributed into a union in the argument type and an intersection in the result type. However, note that for the last rule, it violates the classical interpretation of intersection types. As for example, let's take a look at the identity function. In classical intersection type systems, it can be given this type here, int to int intersected with bool to bool. But the last rule states that this is a subtype of the function type on the right here, int union bool to int intersected with bool. And since obviously we cannot pass something that is either an int or a bool into the identity function and get back something that is both an int and a bool, this interpretation would be unsound. So for any system to admit the last rule for the distributivity of intersection and unions over type constructors, they need to adopt a different interpretation for the intersection types, where the identity function cannot be given such a type in the first place. And this problem also appeared in modern programming languages. For example, Scala-free implements the last rule we see in the last slide. However, they do this without a known theoretical justification. In fact, if you look at the old Scala-free bug tracker, there has been an open issue where a user asks for proofs that the type constructors are distributive in this way, and he specifically notes that the Scala-free compiler implements these kinds of subtyping rules, but the Dot literature doesn't discuss about it. And in light of these issues, we offer a new way of justifying this kind of atypical subtyping. In particular, we do this in the framework of Boolean-Algebraic subtyping, where we are going to present a simple semantic proof of subtyping soundness based on the characteristic homomorphisms of Boolean-Algebraic subtyping. And we prove that the presented homomorphisms indeed characterize the subtyping relation, suggesting a new subtyping decision algorithm. let's look at our language of Boolean-Algebraic Subtyping, which we call MLstruct+. MLstruct+ is a research programming language that features the following: union, intersection, and negation types, as we discussed. And this gives rise to a Boolean algebra of types, where the subtyping order follows all the Boolean algebraic laws presented here, and also their duals. And of course, we have lambda abstractions in this language in the usual way. We also have tag records. For example, we can write a record value equal to 42 tagged with a sum in this way, which can be given a type, the tag type of sum, intersected with the record type, where the value field has type int. And the tag types admits a simple inheritance subtyping relation. For example, the sum tag may be a tag of a text called option. And the records also emit the usual width and depth subtyping. And we also have equi-recursive types in this system. For example, we can represent the list data type as a union between nil and cons intersected with a head and a tail, where the tail part is recursive. In order to eliminate such a union type, we can use tag-based pattern matching, where we inspect the tag of a value and take different branches depending on whether it is cons or a nil. And we denote that this pattern matching is complete by ascribing the bottom type to the scrutiny at the end. And in this system, we can also express extensible variance. For example, in this function mapSum, which takes two arguments, f and ops, it branches on whether ops is a sum. If ops is an instance of sum, then we project the value field out of it and apply f to it. Otherwise, we return ops as is. And to this function, we can give the following type. It first takes a function from alpha to beta, and then takes an object when the object is a sum. It also has a value field, or has some other type beta when it's not an instance of sum. And at the end, this would return the value b. And in this system, we can also express extensible records. For example, take a look at this pair here, which has the first field of type integer and a second field of type int, of type bool. And we denote the type of this pair as tau. And we can use this syntax here to replace the first field of this record with some other value of some other type. And we can type this value as tau with the first field removed, and then intersected with the record type where first is string, and intersected with a tag pair, which turns out to be the expected type, which is identical to the original type, except that the first field has a different type string. And in this system, we adopt an algebraic understanding of types in order to retain principal type inference without backtracking, and enable type simplification and signature subsumption check. In particular, we introduce a few simplifying rules, which includes the distributivity of intersection over function types we've seen before. Also the dual, where the union is distributed into an intersection in the argument type and a union at the result type. We also posit that the union of two records with different fields is greater than the top type. And similarly, the union between a record type and a function type being greater than the top type. And when the intersection of two tag types that are unrelated to each other being less than the bottom type. And let's look at some informal intuition for the simplifying rules. For the third and fourth rule, since the language has no construct to tease apart such a union, we cannot do anything useful to them, so we can effectively equate it to top. And for the fifth rule, since the system only has single inheritance tag subtyping, no value inhabits both T and S for unrelated T and S, so we can effectively equate it to bottom. So thanks to these simplifying rules, we can encode tag and field removal as syntax sugar for Boolean algebraic types. For example, for tag removal, we can encode the removal of a tag T from type tau as tau intersected with the negation of the tag T. We can do this thanks to the following subtyping rules. By the subtyping relation, when T prime is a subtag of T, the T prime tag with T removed is equivalent to bottom. And thanks to the rule 5 before, when S is unrelated to T, S with the tag T removed is equivalent to S. And similarly for field removal, we can encode it as the removal of a field A from a type tau as tau union with the negation of a record type A with type bottom. And by depth subtyping, if we remove field A from a record with field A, we get bottom. We get is equivalent to top. And by the simplifying rule 3 we saw before, if we remove the field A from a record type containing a different field, is equivalent to the record type itself. So suppose that we want to encode some more things as Boolean algebraic rules, as Boolean algebraic types, or we want to perform more simplification for types. Can we add the following rule here that says the intersection of a tag and a function is less than bottom? So it follows the same informal intuition as rule 5 we saw before, since no value inhabits both a tag and a function. The answer would seem to be yes, but in fact, the answer is no, since this rule together with the rule 4 we saw before would be unsound. So in order to illustrate this, let's take a look at the following derivation. A tag is equivalent to itself intersected with top, and by the simplifying rule 4, we can expand top into this union here, and then we distribute the intersection over the union. And by the proposed rule, the second intersection here would be equivalent to bottom. And union with bottom, it's just nothing. And at the end, we have this intersection, which is less than a record type where the field A is tau. And this means that for given any object, we can upcast it to a record containing any field, an arbitrary field with an arbitrary type. And this would obviously lead to unsoundness. So this illustrates that when we admit such atypical subtyping rules, the soundness of subtyping can break in very subtle ways. So in order to justify the soundness of subtyping of algebraic subtyping rules, the original paper on MLstruct took more than 50 pages of convoluted and labored work. So yeah, in this paper, we attempt to present a simple semantic proof in order to simplify this kind of reasoning and reveal more the simple essence of this kind of subtyping. So let's look at the high-level goal of soundness. In the system, we have introduction rules for type constructors, namely abstractions and objects. And if you look at the conclusion of these rules, we can see that they introduce the following type constructors. And symmetrically, we have elimination rules, where if we look at the premises of these rules, they eliminate some type constructors. And in order to prove the soundness of this system, we need to show that only an elimination rule can only eliminate a compatible type constructor, which we see as this correspondence between introduction and elimination rules. However, since we have subtyping in this system, we must also show that subtyping does not relate a constructor with an incompatible constructor. For example, a function type cannot be a subtype of a record type. Otherwise, we'll be able to project a field out of a function, and which would crash at runtime. So we want to make sure that whenever given an introduced type, whenever an introduced type is a subtype of an eliminated type, they can only come from these compatible relations. And furthermore, we want to be able to invert the subtyping relation and get back the relation between the components, namely the contravariance between function arguments and covariance between function results, and also the covariance between record fields. So in simple terms, the soundness of subtyping is to ensure that subtyping does not relate incompatible constructors and respects the variance of constructors. In order to do this, we make use of what we call Boolean homomorphisms, which maps Boolean-Algebraic subtyping derivations into derivations in some alternative Boolean algebra. So what are Boolean homomorphisms? They are mappings that are structural preserving, which means they respect the following laws. They map bottom and top to bottom and top respectively, and they map intersection, unions, and negation types into the meets, join, and the complements respectively. And what we mean by alternative Boolean algebra, it can be the Boolean algebra of types itself or some power sets, etc. What I want to make sure this homomorphism to hold is the monotonicity of them, which states that when tau is less than pi, the image of tau would be less than the image of pi. And to prove this, we need to ensure that every subtyping rule holds after applying the homomorphism. So let's look at an example of how these homomorphisms can help us prove some properties about the subtyping relation. First, we look at what we call shape homomorphisms, which maps to some Boolean algebra where the order is easy to decide. This is used to reject incompatible constructors by the contrapositive of monotonicity. So for example, if we want to show that function types cannot be a subtype of record types of some certain field A, we construct the following Boolean homomorphism, S, which maps to the two-element Boolean algebra where 0 is strictly less than 1. Since we want to prove that functions cannot be subtype of records, we map functions to 1 and subtype and records with field A to 0. And you may notice that there are a few cases that are undetermined. In order to determine this, we look at the monotonicity of this Boolean homomorphism. Most of them already hold, except for the following. In order for this rule to hold, we would need to map records where the field is something other than A to 1. Then monotonicity works in this case. Similarly, for this rule, in order for it to hold, we need to map text to 0. And with this, monotonicity is ensured. And in order to prove our desired property, we use the contrapositive of monotonicity, which states that if the image of tau is not less than the image of pi, then tau is not a subtype of pi. we substitute in a function and a record of field A, and we compute the images of the homomorphisms. And since the premise is true, we can remove it, and then we are left with the desired property. And similarly to shape homomorphisms, we also have something else called a component homomorphism. They map back to the Boolean algebra of types, and they are used to project out the subcomponents of a type constructor of interest. For example, in order to show that this subtyping relation implies tau 1 less than pi 1, when A1 is not equal to A2, we construct a Boolean homomorphism K that maps to Boolean algebra of types. Similarly, there are some undetermined cases here, and in order to determine them, we inspect the monotonicity of the subtyping rules. In order for this rule to hold, functions must be mapped to top, and in order for this rule to hold, tags must be mapped to bottom. And by monotonicity, we have the subtyping relation implies the images are less than, are related by the order, and computing the images, we get the following results, and intersect with top is just nothing, and we can obtain the desired property. In the full soundness proof, make use of 5 families of characteristic homomorphisms, which includes 2 shape homomorphisms and 3 families of component homomorphisms. We call them families of homomorphisms since they are parameterized by tags and record field labels. And it turns out that these characteristic homomorphisms completely characterize the subtyping relation. What do we mean by that? It means that if the order between the images of 2 types hold under every characteristic homomorphism, the types are subtype of each other. And from this, we can derive it gives rise naturally to a new subtyping algorithm, which we denote by subtype of tau and pi. So for every shape homomorphism, if their images are related by the order, and for every component homomorphism, they are related by the order, which we can compute by recursively calling the subtype routine. Then the types tau and pi are related by the subtyping relation. You may notice that this recursive definition has no base type, has no base case. So all we need to do is to add back the base cases where the subtyping relation obviously holds, which are when the left-hand side is bottom and the right-hand side are top. And this algorithm is implemented in the artifacts and is available online and at the following link. In conclusion, based on the characteristic homomorphisms, we presented the following: a simple semantic proof of Boolean-Algebraic subtyping soundness, and a new subtyping algorithm. In the paper, we also showed that the subtyping decision problem is in fact co-NP hard for any system with reasonably behaved unions and intersections, base types, and function types, even when the system does not have recursive types, or even when unions and intersections do not distribute over function types at all. This presentation omits some details about type variables, recursive types, and the coinductive assumption context. And for all of these details, please refer to the paper for them. This is all from me. Thank you.
We have time for one question, and I'll ask the next speaker to set up. Gabriel? Oh, sorry.
So at the beginning, you have shown a subtyping rule that is not correct if you think of the union and intersection as set union and set intersection, which suggests that your union and intersection are something else than set union and set intersection. And my question is, can you give an intuition to the users of how to think of the union and intersection? If it's not set union and set intersection, what is it?
In most cases, you can think of them as set and sets, unions, and intersections, but the main use cases of the atypical rules are for type inference and simplifications, where we want to eliminate the incompatible constructors or cases that cannot be assigned to it, types that cannot be assigned to any values. So from the user's perspective, is basically set, intersections, and unions.
All right, let's thank the speaker again.